Hello everyone, I'm Shreya and today I will be discussing about Pspice, a simulation tool that has fundamentally changed the way we approach circuit design and analysis. Pspice is essentially an advanced version of the original SPICE program which was developed back in the 1970s at the University of California, Berkeley. Pspice isn't just any simulation software, it is specifically designed to enhance the capability of SPICE through user-friendly features and graphical interfaces. Pspice is widely used because it provides a broad spectrum of needs in the analysis of analog and mixed signal circuits, whether in an educational setting, learning the ropes of circuit design, or a professional engineer tackling complex projects. Pspice offers the tools and flexibility needed to succeed. One of the key aspects that make Pspice stand out is its ability to carry out detailed simulation of circuits. It goes beyond just theoretical analysis. PSpice models the actual behavior of a circuit, calculating its electrical characteristics in real time. This means we can describe a circuit to PSpice, sit back and let it simulate the entire process. For a graphical output, it can transfer the data to the program, which can then generate graphs and visual outputs. This feature is incredibly useful for those who prefer a graphical interpretation of the data, making it easier to understand, analyze, and complex circuit behaviors. Let us discuss the benefits of using PSpice in the field of education. PSpice simplifies the complexities of circuit design and analysis, provides a user-friendly platform that makes learning these concepts more accessible to students of all levels. One of the most significant advantages of using PSpice is its ability to simulate circuits without the need of physical components. This not only saves us costs, but also precious time that otherwise would be spent in assembling circuits in a lab setting. With PSpice, students have the freedom to explore various circuit configurations and experiment with different scenarios. This hands on approach allows them to gain valuable insights and learn from the outcomes of their simulations. Moreover, PSpice enhances their learning experience by simulating complex electronic phenomena from transient responses to frequency analysis. Students can witness and understand these concepts in action, deepening their comprehension of circuit behavior. Another standout feature of PSpice is its extensive component library. From basic resistor and capacitors to advanced semiconductor devices, PSpice covers a wide range of topics catering to the needs of students at every stage of their learning journey. Now, let us talk about the use of PSpice in various industries. So, PSpice sets the standard for accuracy and flexibility in circuit design modeling. Before a single prototype is built, engineers can simulate and tweak designs, ensuring they are on the right track from the get go. This leads to our next point: cost efficiency. By identifying potential issues early in the design phase, PSpice significantly reduces both development time and costs. This early detection system is invaluable in keeping projects within budget and on schedule. Lastly, the impact of PSpice extends across various industries, from consumer electronics to aerospace and automotive. Its powerful analysis tools are key in optimizing circuit performance, readability, and pushing the boundary of what is possible in electronic design. This image shows the home screen or schematic for PSpice, a circuit simulation software tool as we know. The toolbar of the top contains menus for File, Edit, Draw, Navigate, View, Options, Analysis, Tools, Markers, and Windows. The left-hand side of the image contains the library of components that we can add to the schematic. The right-hand side of the image is the drawing area where we can create our own circuit. The bottom of the image contains a status bar that shows the information about the current selection. Overall, this shows the basic layout of the PSpice interface. To simulate a circuit design in the schematics window, we will need to obtain the paths required for it, which we can get from clicking this Get New Part in the menu bar. So when we click on this, we'll be taken to this window as seen here. And here we can enter the circuit part, circuit number which we require, circuit will be present in the schematic window. I'll take the example of simulating a full adder circuit which requires a XOR gate AND gate. So the circuit number for AND gate and XOR gate is different. The number for XOR gate, as you can see here, is 7486. When we type it in the search bar, we will be shown with this, and this will be present in the schematics window. Now let us talk about why do we need to use digital clock. A digital clock provides precise timing for digital circuit operations, which is essential for ensuring that your circuit functions are as intended. They can provide consistent time basis for sequential logic and event coordination, simplifying design process and making it easier to identify and troubleshoot potential issues. Digi clocks can also be used to enable testing and validation of circuit behavior under various frequencies, helping it to identify design limits, timing, margins, and potential issues before you even build a prototype. Finally, they can facilitate power consumption analysis for energy efficient design development. Now, let us discuss how do we add a digiclock to our circuit. Open the Get New Part window and in the part name block type Digi. Select the DigiClock from the list given and then click on Place and Close. Once the DigiClock is placed on your schematic, we can connect it to the other components in the circuit as needed. After adding the digiclock to the circuit, we must set the on time and off time for it. We can set the on time and off time by specifying the parameters in the digiclock properties dialog blocks. The time is specified in nanoseconds. The sum of the on time and off time must be equal to the period of the clock signal. We can use digiclock to create clock signals with a variety of periods and duty cycles. The delay parameter can also be used to specify a delay before the first transition of the digital clock. The digiclock component can be used in both transient and steady state simulations. The image on the right shows the dialog box that is prompted when we click on the digiclock icon so that we can enter the on time and off time. Now, I would like to talk a bit about on time and off time and why it's necessary. So, on time is essential for synchronization of digital operations. It ensures that the signals are aligned perfectly, facilitating seamless communication between the components. This synchronization is the backbone of reliable digital system. Different components require different specific pulse widths to operate correctly. By adjusting the on time, we can ensure a circuit communicates effectively with all its parts, maintaining the integrity of overall system. Another key aspect of on time is its impact on signal duty cycles. By controlling the on time, we can fine tune the duty cycle, directly influencing the circuit performance. Furthermore, on time enables us to test how circuits respond to various signal durations. This capability is invaluable for designers looking to create robust systems that perform reliably under different conditions. Now, moving on to off time. Off time is crucial for achieving precise timing and synchronization in digital circuits. It dictates the idle periods between the active signals, ensuring that the operations are perfectly timed and synchronized across systems. This precision is essential for smooth functioning of complex digital systems. Off time also allows us to experiment with various duty cycles, enabling the optimization of circuit performance for different applications. By fine tuning the balance between on time and off time, designers can achieve the desired performance characteristics, whether it's maximizing efficiency or minimizing power usage. Moreover, understanding and controlling off time is critical for testing circuits under conditions where signal is inherently absent. This testing ensures that circuits can handle real world scenarios where signal presence may vary, guaranteeing reliability under diverse conditions. Lastly, off-time helps in accurately mimicking real-world signals that exhibit specific off-time characteristics, whether it's simulating communication protocols or emulating environmental sensors. The ability to replicate these signals in our designs invaluable for creating realistic and effective solutions. In conclusion, off time and on time is not just parameters, it's powerful tool in the digital design process, enabling precision, efficiency, realism in our circuits. Understanding its impact in applications is key to mastering digital circuit design. So another component which we must add so that our circuit functions normally and properly is a voltmeter. We can access it from the toolbar and its icon looks as in the image on the left hand side. So voltmeters allow us to observe the voltage between any two points in a circuit. This might seem basic, but it's fundamental to grasping how a circuit functions under various conditions. It's like having a conversation with your circuit where voltage levels reveal its health and efficiency. Moreover, voltmeters ensure that the components operate within their specified voltage ranges. This is crucial for both the safety and functionality of the circuit. By regularly checking these voltages, we ensure that our design not only meets the theatrical expectations but also complies with the real world operational standards. When it comes to circuit analysis and debugging, voltmeters are our eyes, identifying issues that might not be immediately apparent. Observing voltage levels throughout a circuit helps us to quickly pinpoint areas of concern. It's detective work where subtle clues like unexpected voltage drops can unveil hidden problems, from excessive resistance to faulty components. These insights allow us to not only fix the existing issues but also optimize circuit performances. By analyzing voltage levels in different parts of the circuit, we can make informed decisions to enhance efficiency, reduce power consumption, or improve response time in a circuit. Another important feature available in Pspice is label. We can double click on the wire or any component we want and a window appears as a result. We can name the component or the wire whatever we want for simplicity. So, why are labels important? We need labels to enhance the clarity and readability of the circuit. It's like a complex circuit which doesn't have any label is like navigating a bustling city without street signs. Label provides us with a map, making it easier to understand and navigate our circuits, no matter how complex they get. But it's not just about making things easier to read. Labels simplify our analysis by clearly marking points for measurement and comparisons. They save us time and reduce the risk of errors. It's like having a reliable assistant who always knows where everything is and can bring it to us without any hesitation. Moreover, labels are champions of modularity and reuse. In the world of circuit design, where time is often of essence, being able to quickly identify and reuse components or subcircuits is invaluable. Labels make this possible, streamlining our design process and fostering innovation. Communication is another area where labels shine. When working on a project with a team, having a common reference point is crucial. Labels provide that, ensuring that everyone is on the same page, which in turn enhances collaboration and minimizes misunderstandings. Lastly, labels continue and contribute to efficient simulation control and documentation. They allow us to keep track of our work, making simulations easier to manage and understand. In documentation, labels serve as key references, ensuring that everyone who reads our work can follow along without getting. So this is how the final circuit is supposed to look like. We will take the example of full adder and half adder circuits. As you can see, both the circuits are complete with labeling, digiclock, voltmeters, so that when we simulate, we get the required output and the desired output as we wish. So these circuits are labeled so that we can understand them correctly and we can reuse some of the sub-circuits here. The digiclocks are attached wherever required. The voltmeters are placed at appropriate locations so as to monitor the voltage that passes through them. A wire connects all the components, and upon simulating, we will get the required waveform. Once our circuit design is complete in the schematic, we need to define the simulation type, example DC analysis, transient analysis, etc. and specify the parameters like input voltages, sweep ranges, and simulation time. How to run the simulation? Pspice then performs the simulation based on our defined parameters and calculates the voltage and current at various points in the circuits. After this, we can analyze the results. The Pspice presents the simulation results in graphs and tables, allowing us to visualize and analyze the circuit behavior such as voltage waveforms, frequency response, and power consumption. Here in this slide, for the circuit of binary adder, we use transient analysis. We must define the timestamp for it and simulate the program. Once we simulate the timestamp like on time, off time, and delay, this is how the waveform for half adder should look like. There is a flat line for low signal, and once the signal is high, we see a spike. This is how the waveform for full adder looks like. There's a spike when the signal is high, else it is a flat line. So both of these represent the truth table of how full adder and half adder functions. At its core, Pspice boasts as an extensive library that is nothing short of a treasure trove for any designer. Imagine having access to a vast array of components at your fingertips ready to be deployed in your simulations. This library not only accelerates the design process but also opens up new realms of possibilities for innovation and creativity. But PSpice doesn't stop there. It brings to the table sophisticated mixed signal analysis capabilities. This means we can seamlessly blend analog and digital components within the same simulation, reflecting the complexities and richness of real world systems. It's like having a bilingual interpreter in a multilingual conference, ensuring smooth and efficient communication across different circuit languages. One of the standard features of Pspice is its advanced testing methodologies, including Monte Carlo analysis and parameter sweeping. These tools are akin to having a crystal ball, allowing you to foresee how your circuits will behave under a myriad of conditions. They enable us to fine tune our designs to perfection, ensuring reliability and efficiency. Understanding and optimizing circuit behaviors under diverse conditions are no small feats. However, PSpice makes this daunting task not only manageable but also intuitive. It empowers us to delve deep into the intricacies of circuits, unveiling insights that guide us towards precise and efficient optimization. The role of simulation tools in the design process cannot be overstated. PSpice stands out as critical ally facilitating pre-prototype design validation and optimization. It's like having a rehearsal before the big performance, ensuring that our design hits all the right notes before it materializes into a physical prototype. Moreover, PSpice is a cost saver, time saver, and an error minimizer. It is diligent proofreader that catches mistakes before they become costly errors. The strategist that streamlines the path to market and the guardian that safeguards our. Lastly, let's talk about the realism PSpice injects into simulations. With tools like digiclock, voltmeters, labels, wires, it replicates real world systems with astonishing accuracy. This ability is not just impressive, it's instrumental in ensuring that our designs not only work on paper but thrive in the real world. In summary, PSpice isn't just a software, it's a pivotal force in the electronic design arena. It empowers us to push the boundaries of what's possible, ensuring that our innovations not only meet but exceed the demand of the modern world. I would like to conclude this presentation through the and capabilities of PSpice. It's been a privilege to share insights and explore how PSpice continues to shape the landscape of electronic design and analysis.